So I've given the task to talk about axion physics, and I start with a disclaimer. So I mainly concentrate on the QCD axion, on the axion which solves the strong CP problem, but some or many things which I'm talking about can also be used or exploited for axion-like particles, or often called ALPS. So now I have to find out how I go to the next slide. Okay. So the axion is with us already since nearly the beginning of quantum chromodynamics. So in the early 70s, quantum chromodynamics as the non-abelian gauge theory of describing the strong interactions, and in the original original formulation, it appeared in the action of QCD, not only the gauge covariant kinetic term for the quarks and the gauge covariant kinetic term for the gluons, and these two terms they both contain all the interactions which has been successfully tested at colliders and which are the basis of the description of strong interactions in collider physics. However, shortly after the development of the theory, people like Bellarmine et al., Geratov, Kellen, and Shakib and Rebbe, they pointed out there's a further term which is possible to write down for at the renormalizable level, or at dimension 4, which contains the gluonic field strength contracted with its dual, and this term was originally not taken into account because it's a total derivative. So, however, it has been emphasized, or it has been found that in fact the space-time integral of this total derivative is a topological quantity. It gives the topological charge, or the Pontryagin index of gauge field theories, and therefore this term could have a meaning in non-perturbative processes, which cannot be described by the Feynman diagrams, which are shown here on the slide. So, and because these are integer, this gives an integer number after the integration over the space-time volume. So the strength of this term is measured by an angle, the so-called theta angle, and so this means that quantum chromodynamics is not only determined by the strong coupling and the quark masses, but there's a further parameter, namely the theta angle, which can be an hourly value between -pi and +pi, and so it's just now a matter of determination of this angle in order to know to define or to know what is quantum chromodynamics. So of course, because it's a total derivative, and because it cannot be described by perturbation theory, so observables which depend on this extra parameter, on this theta angle, they must be calculated non-perturbatively. So, but first of all, let's see what kind of effects this theta angle leads to. So if one just writes this topological charge density in terms of chromoelectric fields and the chromomagnetic fields, then one sees it's just E dot B, and then it's easily seen that E dot B violates time reversal invariance and parity, and thus CP. So this term will lead to strong CP violation in flavor diagonal interactions. Now, the most sensitive probe of time of T and P violation in flavor conserving interactions is the electric dipole moment of the neutron, which is directly proportional to T and P violation. So, already shortly after the appearance of this theta angle, or the discovery of this theta angle, there had been the first estimates by chiral perturbation theory, and later and now much later. So the most recent calculation has been determined by QCD sum rules. So the QCD contribution, or the contribution from this theta term to the dipole moment of the neutron, should be of the order of 2.4 times 10 to the minus 16 theta bar E centimeter. So, oh, excuse me, terrible. 10 to the minus 16 E centimeter. Now, a comparison with the experiment, and the latest experiment was reported now this year, gives an upper bound on the dipole moment of the neutron of 1.8 times 10 to the minus 26 E centimeter, and then comparison the prediction with the experimental upper bound. We infer that the theta bar is less than 10 to the minus 10, and this is one of the puzzles, higher of something like natural puzzles in the standard model. Now, shortly after this, after the pointing out that there is this puzzle, that the theta bar is so small, Roberto Peccei and Peccei-Quinn proposed a solution to the strong CP problem, which is, in a sense, it's in a nutshell, they propose to replace the theta parameter by a dynamical field, by a dynamical theta field. So the idea is to add to the standard model a Nambu-Goldstone field. So it's like an angular field, A of x divided by f of a, where f of a is, so to say, the decay constant of this Nambu-Goldstone field, respecting a nonlinear realized symmetry, shift symmetry, broken just by the coupling to the gluonic topological charge density. So there should be a term so the effective interaction of this theta field with the topological charge density in QCD should be just such a linear term. Then clearly one can eliminate the QCD theta parameter by a shift, and then QCD itself solves the strong CP problem, because the effective potential at energies much below the lambda QCD has an absolute minimum at theta equal to 0, and thus predicts a vanishing WEF for this field, which has been so clearly shown by Waffa and Witten. And so this potential can be even calculated in chiral perturbation theory. And you see below on this slide, you see the dependence of the potential of the field on this theta parameter. It has an absolute minimum at 0, and therefore so the QCD would solve the strong CP problem itself if the theta parameter is replaced by this Nambu-Goldstone field. And of course, so the curvature around this minimum, so there will be a particle excitation, and this particle excitation has been dubbed the Axion, And it's a pseudo Nambu-Goldstone boson because, of course, there is a second derivative, so it has a mass. Around it, the mass is given by the topological QCD sustainability in QCD, which is it's the 2-point function of this topological charge density, and this determines the mass of this axion in terms of the decay constant. So the mass will be given by the square root of the topological density sustainability divided by the decay constant, and the recent precise determination both in chiral perturbation theory and also in lattice QCD gives now the mass, that the mass is of the order of 5.7 milli-electron volt for a decay constant of the order of 10 to the 9 GeV. So it's a very light particle. It's one of these light bosons, which, as we will see later, could play the role of the dark matter. So how to get such a Peccei-Quinn extension of the standard model? What is the simple way to get such a dynamical theta field? The simplest way is to add a complex singlet to the standard model, featuring a spontaneously broken U1 symmetry, and then the particle excitations will be, of course, the following: that the mass of the particles of the particle, which is the excitation of the modulus, will be of the order of the symmetry breaking scale and V Peccei-Quinn, and the mass of the particle excitations of the phase will be 0. So it will be just a Nambu-Goldstone boson. Now, if one adds now colored fermions in the model carry Peccei-Quinn charges such that the U1 Peccei-Quinn symmetry is broken due to a gluonic triangle anomaly, like illustrated on the slide, then the low energy effective field theory at energies above lambda QCD but below the electroweak symmetry breaking scale will look exactly like the required coupling of an axion field, namely it will be just linear interacting with the topological charge density in QCD. And from that we can now read off what the axion decay constant is. The axion decay constant is just the Peccei-Quinn symmetry divided by the number of, so to say, by the normalization of or the number of anomalies. So so there are different, so explicit models have been of such a so-called invisible axion model have been developed by Kim, Schiffman, Weinstein, Sakharov, and by Ziditsky, Dine, Fischler, and Srednitsky, and then many more. Now, clearly, so the axion couplings to the standard model at energies below the QCD scale then will all be inversely proportional to this decay constant. And so there will be, of course, a guaranteed interaction with the nucleon dipole, electric dipole moment. There will be a coupling to photons, and there will be coupling to the spin densities in the theory. And the coefficients of these couplings, they are either fixed for the electric dipole moment coupling, just by QCD itself, and then for the couplings to photons and to fermions and to nucleons, they are partly fixed by the mixing of the axion with the pion, but there are also model dependent factors which are different in different models. So the coupling to the electron will be very model dependent. But as one sees, so the axion has the property, if this decay constant is, or the Peccei-Quinn symmetry breaking scale is very large, then the axion is very weakly coupled to the standard model, and it's also very light. However, so we get no clue from this model building. We get no clue about the size of the axion decay constant or the size of the mass. The strong CP problem is solved for any value of Fa. However, now shortly, so the axion was initially invented by Roberto Peccei-Quinn in a particular model where the axion itself had the weak, so the decay constant was of the weak scale. So this was very rapidly excluded experimentally, and then these invisible axion models with the extra complex singlet were introduced, and so first it was thought that this could evade all the limits from experiments, and also gets also very strong constraints from astrophysics and so on. However, also not very shortly, not very long after the discovery of the axion, it was realized that the axion cannot hide completely, because it necessarily leads to it necessarily can make so the larger that, or the smaller the mass, or the larger the decay constant, the more axion dark matter is produced. So how does this go like? So now I talk a bit about the vacuum realignment mechanism. So suppose now you have such a invisible axion model. Then at high temperatures, the symmetry is the Peccei-Quinn symmetry is restored, but at energies of at temperatures of the order of the Peccei-Quinn scale, the phase transition takes place and the axion comes into play. So at the beginning, the axion is essentially massless, because these QCD effects they appear only around temperatures of the QCD scale. The axion will take random initial values in causally connected domains, and then when the expansion rate of the universe is of the order of the axion mass, which itself depends on the temperature, then the axion field will start to oscillate around the minimum of the potential, and it will behave like cold dark matter. So essentially, so its equation of state will be around 0. So now, very recently, there have been important progress in order to at least to determine the amount of axion dark matter produced by this vacuum realignment mechanism, in the sense that both the Hubble expansion rate and the mass of the axion have been determined more or less on the lattice or there was important QCD input from the lattice. The equation of state is determined essentially by the Hubble expansion rate as a function of temperature around the QCD the QCD scale, or the QCD crossover is determined essentially by the equation of state, and so the number of entropy and capacity, heat capacity, and energy density contributions, which have been determined recently quite with a very small error bar, and the topological sustainability, which determines the axion mass, has been determined also quite using new lattice results over the relevant energy range, and this made it possible to make so at least to calculate the axion abundance quite reliable. So, but nevertheless, it depends. So there are further uncertainties or environmental facts which make still the calculation of the prediction uncertain. Now there are two main scenarios how the Axion dark matter is determined, which relate to also to inflation. Namely, if the Peccei-Quinn symmetry is broken before or during inflation, which means that if the Axion decay constant is larger than the Hubble expansion rate and during inflation and not restored afterwards, then the Axion cold dark matter density depends on a single initial value in the patch, which becomes the observable universe, and on the decay constant. So so here the result is shown, which means that that there is one one has this initial theta I value, which is environmental parameter, so to say, and the axion mass or the axion decay constant, which you can interchange, which is other as you wish. So so one can have in this scenario, you can have for all masses you can get you can describe the dark matter relic density, the observed relic. You can match the relic observed relic density. However, if FA is much larger than 10 to the 12 GeV or so, then you need an initial value which is smallish. So, for example, for a gut scale FA, you have an initial value of a few times 10 to the minus 3, which you could also say, I mean, is it a fine tuning? But it's like that. On the other hand, if you have a post-inflationary Peccei-Quinn symmetry breaking scenario, then you have to average over the random initial axion field values, and so there is no dependence anymore on this initial parameters. But then, of course, there will be a lower bound on the axion on the axion mass, or an upper bound on the FA. Because otherwise you have an overabundance of axion dark matter. So this lower bound is around 25, 26 microelectron volt. Now, moreover, in this case, if you have post-inflationary Peccei-Quinn symmetry breaking, axions are also produced by the collapse of the network of topological defects like strings and domain walls, which introduces very large uncertainty, because at the moment, so these string and domain wall networks and so on cannot be simulated at the real physical sizes, and therefore we have there and you can also have so if you have I mean, there's a huge uncertainty. So one to take home from this is that it's still the axion mass can still be between 25 microelectron volt and 40 millielectron volt, and we cannot. We cannot make this this uncertainty really smaller. So it makes sense, but the lower bound is more or less the lower bound is solid, but the upper limit is still uncertain. Now, to summarize. So the dark matter axion mass really spans a huge range in masses. So say from 10 to the minus 6 microelectron volt to 10 to the 4 microelectron volt. Fortunately, so this gives also a strong motivation for current and upcoming axion dark matter experiments. And just in the recent few years, there has been a lot of excitement and a lot of new players in Axion experiments, which use very different techniques from nuclear magnetic resonance techniques like CASPR, which directly looks for oscillating electric dipole moments, like abracadabra, which is using a superconducting ring experiment. There are microwave cavity experiments, which are really operating now at the moment, like ADMX, Haystack, and so on. And there are newcomers at the high end, which are motivated by the post-inflationary symmetry breaking, like MadMax and Brass and Quarks and so on. So just in the last few minutes, I just summarized these searches for dark matter axions. Now, the classic experiment are based on microwave cavities placed in a magnetic field. So Peccei-Quinn was proposing them, and this gives from our recent update of the particle data group review of particle physics. This gives the limits which have been obtained now in the coupling to the photons versus the axion mass, and ADMX has really digged deep in the QCD axion predictions. There are now many other experiments currently in construction, like CALTASK and CAP at the Center of Axion and Precision Physics in Korea, and proposed experiments like CLASH, Axion, and YAXO dark matter, and so on. And these microwave cavity experiments, but you will see they end somehow at something like 40, 50 microelectron volt, and they don't cover really the post-inflationary scenario. And in order to cover this post-inflationary scenario, there have been proposals like the one which I'm now just mentioning. These are to search for axion dark matter using, instead of microwave cavities, it's using dish antennas. This is based on the fact that a magnetized mirror in an axion or ALP dark matter background will radiate photons. Now, if you just have a mirror and collect this signal, then you will get a very small power per unit area of 10 to the minus 27 watt per meter squared in the relevant parameter range, even if you have a 10 Tesla magnetic field. However, there have been ideas now to boost these signals by adding in front of such a magnetized mirror, by adding dielectric disks with a lambda half spacing in front of the mirror. Then you can get constructive interference of the photon part of the wave functions. And such an experiment is currently has been proposed. This is the so-called MadMax experiment, which wants to use a boosted dish antenna. So the conceptual design report has been published. A prototype will be employed at CERN next year or this or next year. Now the Corona delays many things, of course, maybe also this one. And the full-scale experiment is foreseen to be done at DESY starting in 2025 or 2026. Now, with this kind of experiment, one aims to probe into the axion, deeply in the post-inflationary axion dark matter scenarios. Searches for solar axions have been done already quite for a while. So one is looking for a solar axion and ALPS produced by two photon process in the core. But also, of course, ALPS are also produced if there is a significant axion electron coupling. They are also produced via Bremsspannung and other and Compton and atomic recombination de-excitation processes. And the idea was then also proposed originally by Peccei-Quinn to look for Alps solar Axion Alps conversion to photons in a magnetic field by pointing a magnet towards the sun. And so the CERN Axion solar telescope was the biggest of these kind of experiments, the most sensitive of this experiment. And now a successor for this, the International Axion Observatory, IAXO, was proposed, which proposes to have a large toroidal 8-coil magnet with a length of 20 meters and quite so everything is a bit scaled up in comparison to the IAXO experiment. The proposed site is DESY, but before one can start with that, we are doing now a prototype for IAXO, the so-called baby IAXO, which uses just 2 bores of dimension similar to the final IAXO bores, but similar detections things, and it's already it's nearly funded. The Hera South Hall is being prepared for baby IAXO. The preparations have already started now, and the data taking may start in 2024 and 2025. And so baby IAXO will really probe by a factor of more than 10 in comparison to the cast limits, and it will dig into the milli-electron volt mass QCD axion. And IAXO will go even deeper, of course. Finally, so as a last point, I will also mention the light shine through wall searches at DESY. So with ALPS, the any light particle search at DESY, we had produced 2009 the best direct limits on light axo-like particles in a poorly laboratory experiment. And now at the moment, as we speak, the successor of this experiment is built at DESY. So it's called the ALPS-2, which will increase the sensitivity in photon coupling by a factor of more than 10 to the 3 by exploiting 12+12 straightened Hera magnets and optical cavities both at production and regeneration sites. So in this letter, we are using many things which have been developed for LIGO or advanced LIGO, and we are collaborating with people from the Albert Einstein Institute in Hanover and the University of Cardiff and University of Florida, which are also members or participating at LIGO. So this experiment, so the Hera tunnel is already cleared by 300 meters. 24 magnets are straightened and tested, and magnets are installed, and everything is on track for data taking in 2021 with ALPS-2. And ALPS-2 will be the first purely laboratory experiment which exceeds the helioscope's bounds and also the bounds from energy loss considerations of horizontal branch stars by nearly an order of magnitude. So conclusions, I think Axion extension of the standard model are very attractive. There is a boom in Axion searches. Large part in Axion Alp parameter space will be tackled in the upcoming decade. And if 100% of the dark matter consists of QCD axions, I think one of the dark matter axion experiments is likely to see a signal in the upcoming decade. Stay tuned.
All right. Well, thank you for that wonderful review. We do have a couple questions in the Q&A. Our first question comes from Howie Bear. If you introduce a new large Peccei-Quinn energy scale, do we need to worry about the Higgs mass being dragged up to the new scale?
I mean, I think Tim has already answered this. So, so it's of course, and then we have to you could say we have to stabilize another scale. So I mean, but it's like we should of course wonder why we have then why we have these hierarchies. But I have no answer about that, unfortunately.
All right. Our next question comes from Carlos Wagner. To give a solution to the Strong's TP problem, we need a coupling of the axions to gluons, of course. Yes. Most searches, however, use the coupling of the axions to photons.
Yeah.
How can I fix this coupling in a model-independent way? Should it be necessarily induced due to the mixing with pions?
Yes. So this was this term which I showed on my slide. This was this 1.92, this number. This was from the mixing of the pions, and the rest, the E/N factor before, was from the mixing with the gluons. Was from the mixing with the pion. So this was, let me see. You can already ask this in the next question, but here it is. I don't know why this is so slow. So the E/N is the so this is the model dependent factor. So in the KSVZ model, which doesn't introduce new things, and if you introduce just one extra quark, N is equal 1 and E is equal to 0. So Ca gamma is minus 1.92. So this is fixed. Oh, I don't hear you, Christopher.
Sorry. One more from Alexis Placencia. Is it possible to distinguish between the KSVZ and the DFSZ axion in some of these experiments? For example, by measuring coupling only to electrons.
The nice thing about the solar helioscope is that at least you can measure the product of the axion photon times the axion electron coupling. If there's an extra axion electron coupling, and you can distinguish that. So I mean, so but in ALPS you can only measure the axion photon coupling. So we need several experiments. And there's another experiment which I didn't mention, but there is, in principle, you can also do looking for the fifth force, where you could measure, for example, the coupling of the axion to the electron. But this will only work at a certain mass range, but also in the milli-electron volt range, this can work. This is the experiment Ariadne, which I was mentioned.
All right. I want to jump to this question by Lucien Hotier. Hi, Andreas. Thanks for the nice talk. You maybe give a little bit more detail about these interferences used together with magnetized mirrors. Is this something like the Laue or Bragg reflection effects, or is it something else?
No, it's like if you, maybe I should. Can I don't know. So at each of the surface, intersurface between the vacuum and the dielectric surface, you have outgoing photons and reflected photons and so on. And in the end, you can get the constructive interference you get best if you have a lambda half difference spacing between these mirrors, and then you get, so to say, an n squared enhancement, n squared boost factor, where n is the number of mirrors or dielectric disks.